Hello, this is Professor Rai in section Change Focus in More Ways. This is the last section in Math 132. You guys have made it. Congrats. This is an actually very fun section because it talks about riddles that you guys have seen on Facebook or in newspapers, specifically about the problem-solving strategies that are needed to solve these riddles. Most riddles are created in a way that they would seem so easy to solve. However, once you start solving them, you'll find yourself stuck at some point. This section, or the main idea of this section, is to show you how, in most cases, it would be so much easier to change your focus in order to solve a problem. We might have to change our point of view, solve a complementary problem, or even change the whole representation of the problem in order for us to solve it. Let's look at this maze for an instance. If you want to solve this maze directly, you would start from the beginning, and you will see that you have three ways to go. However, if you change your point of view, you can look at the end, and you can see that you only have one path from the end to the start. So if you start from the end, you can solve this maze in a way much easier and faster way than if you started from the beginning. Most of the problems in this section will deal with this idea, how to change our focus in order for us to solve the problem. The first part of this chapter is called Change Your Point of View. So let's see this riddle. Without lifting your pencil from start to finish, draw 4 line segments through all 9 points. So give yourself a minute. Try to do it by yourself before watching the answer. Most of us will look at this problem and try to draw the lines within the square itself. Even though we're not told that we have to stay inside the square, we are programmed to use these points only. However, if you change your point of view, you'll find that the solution requires you to go beyond the square. Let's see the solution. You see, the solution did exactly what we're asked to do. We drew 4 line segments without lifting our pencil, and we have passed all the 9 points. So we actually needed to change our point of view in order for us to leave the structure of the square and go beyond it to actually solve the problem. So let's see an example. Jack left his home in Austin and drove to San Antonio. On the way there, he drove 40 miles per hour. On the way back, he drove 60 miles per hour. What was his average speed? Now remember, speed is distance over time. And even though we're given two speeds, we cannot find the average unless we know the total distance and we know the total time. So a first response would be 50. You would take, for example, 60 and 40, take the average of that, and that would be 50. However, that answer is wrong. As I said, you need to know the total distance and the total time to solve this problem. But we're not given those information. So here's what we're going to do. We're going to change our point of view and make up distances. And you will see that no matter what number you choose, you will actually get the same answer. So let's try this. A good distance to use would be 120 miles. If you use 120 miles as the distance from Austin to San Antonio, then it took Jack 3 hours to make the trip to San Antonio, traveling at 40 miles per hour. Why? Because speed over distance equals time. So 120 divided by 40 equals 3. On the way back, he traveled 120 miles at 60 miles per hour. This trip took 2 hours. Again, 120 divided by 60 equals 2. This means that the total distance would be 240, So if you're adding, going back and forth will be 120 plus 120 will be 240 miles. And the total time would be 5 hours. Again, why 5? Because we have 3 hours going forward and 2 hours going backward. So now you have 240, this is the distance, divided by the time, you will get the speed. So 240 divided by 5 will be 48 miles per hour. And this would be the average of speed. So let's say you chose a different number than 120. Let's say you chose 180. Let's do this. So going forward, the time needed will be 4.5 hours. Again, try. Divide 180 divided by 40. Distance over speed gives you time. On the way back, he is traveling at the speed of 60 miles per hour. So 180 divided by 60 will be 3 hours. So now the total distance will be 180 plus 180, and that's 360 miles. And the total time will be 4.5 plus 3, and that's 7.5 hours. Divide the distance over time, you will get the same number. And that's so fascinating, even though we're making up values. And it seems that we are making up values, but we are actually keeping the same structure. We are still using the formula that says that distance over time equals speed. And we are generating these values from the original speed that we were given. And that's why no matter what number you choose, and try the weirdest number, you can try 119, or you can try whatever number that you want, you will still get 48 each time as the average of the speed. The second part of this section is called Solve the Complementary Problem. Sometimes it is easier to try to find the opposite instead of solving the problem itself. This approach is called solving the complementary problem. It's another way of changing focus. Rather than solving the stated problem, solve the complementary problem, then use the results to solve the original problem. Use this strategy to solve the next 3 examples. Consider a problem from probability. How many ways are there to roll 2 dice and have the sum be a 1-digit number? Instead of answering this question, answer the opposite question. How many ways are there to get a sum of 10, 11, or 12? Keep in mind, trying to solve this problem directly will make us consider all the sums from 1 through 9. It's much easier to only consider the sum of 10, 11, or 12. We can get 10 by rolling 6 and 4, 5 and 5, or 4 and 6. And we can get the sum of 11 by rolling 5 and 6, or 6 and 5. And finally, we can get 12 by rolling 6 and 6. So there are 6 ways to roll 10, 11, or 12. Therefore, because there are 36 outcomes when rolling 2 dice, there must be 30 ways to roll a 1-digit number. Example 2. Find the area of the shaded region. This is a problem that you've seen in Math 131 and earlier this semester. It's much easier to find the area of the non-shaded part rather than finding the shaded area. We can do this by finding the area of the square first, which is 10 times 10, so that's 100 square units. Find the area of the circle itself. Since the radius is 5, the area of the circle would be 25 pi square units. Thus, the shaded area is 100 minus 25 pi, which is 21.46 square units. Example 3. A big regional tennis tournament in New Orleans drew 378 entries. It was a single elimination tournament, in which a player was eliminated from the tournament when the player lost a match. How many matches are played to determine the champion? You could start solving it directly, but it will take time. Let us look at the complementary approach. There is only one winner, so everyone else must lose. Each match produces a winner and a loser. The winner goes on, but the loser is eliminated. When the tournament is over, all players but one have lost. So there must be exactly that many matches, one less than the number of players in the tournaments. Thus, there are 378 minus 1, which is 377 matches in this game. The last part of this section is called Change the Representation. Change the representation is a strategy that combines changing focus with some other strategies. Generally, you use the strategy of drawing a diagram when you change the representation, but other strategies are also possible. Let's see an example. Example 4. Using 6 toothpicks, make 4 triangles of the same size. Now let's try to do this together. You would start by drawing a triangle, which will need 3 toothpicks. And then you might be adding another 2, and you'll find that you've already used 5 of them, and you only had 2 triangles drawn. For this to happen, we need to change the representation from a 2-dimensional point of view to a 3-dimensional point of view. If you put the 6 toothpicks this way, you would have a tetrahedron, which is a 3D shape that consists of 4 faces of equilateral triangles. So you have achieved the goal by changing the whole representation. And that's it for this section. The homework has 4 problems that are very similar to the examples solved in this section. And that's it. Take care. Bye.